Hey everybody, it's Rick Uzzi. I'm here with Carlos Bustamante today. We're here for Technology Tuesday. And last week we started our series and it's on proactive network maintenance. And I kind of gave a rundown on what pre-equalization is and PNM and how they work together. And one of the things that I talked about that's very kind of key to PNM is microreflections, because that's what you can kind of identify when you're looking at the differences between the pre-EQ coefficients. So we're going to talk about that today. As I mentioned last week, if you want to ask a question while we're live, go ahead and ask it, and we'll check that out and see if we have any questions during the broadcast, maybe or right at the end. And you can still ask questions after as well on our YouTube page. So Carlos, microreflections, why don't you give us a quick rundown, and I think we're going to go through some slides as well that you can see as we do this.
Absolutely. So for today, we're going to go through a concept, and also we're going to go over a couple of PNM terminologies. So the first one being impedance mismatch. So let's go through the slides, if you will.
Okay. All right. So just a second here.
All right. So essentially, what we're going to talk about is what is an impedance mismatch, and what does it mean? So let's go back this way. All right. So the concept that I want to transmit to you is impedance mismatch. And what we have here is the following. So essentially in a cable television network, you're looking for the ideal world would be a homogeneous characteristic impedance of 75 ohms. So from the head end through your network infrastructure all the way to the customer prem, ideally 75 ohm characteristic impedance. Anything that is dissimilar to the 75 ohms will be labeled impedance mismatch. So what I have here on this figure, as you see in the slide here, is what I want you to take away is that there's a flow of information or signal from left to right, where there is a 75 ohm environment hitting another cable segment that just simply is not 75 ohms. The fact that there is dissimilar characteristic impedance will cause a microreflection. So let's draw an analogy here that I'd like to use, and I take a lot of artistic liberties on this particular analogy. So let's say it's a sunny day and you're outside and you're going to look out the window, right? You're looking outside the window at the parking lot, and you're looking through a window that has what's called the glass air interface, two dissimilar materials. So when you're looking out the window, you are looking outside, but don't you see a faint reflection of yourself? So that is the analogy that I like to use of what a microreflection is. Because there are two dissimilar materials touching one another, this will cause a microreflection. Okay?
Okay.
All right. So an impedance mismatch, again, will cause a microreflection. So let's talk a little bit about that. Let's go to the next slide, if you will. All right, so what will cause a microreflection? Anything from a damaged or missing end-of-line terminator, loose connector, loose center conductor seizure screw, unused tap ports that may not be terminated, kinked or damaged cable, that type of thing, damaged actives or passives. These type of things could cause microreflections. So what we have here is the following. In the image in the upper right, we see the house to the right of tap 17. And let's assume that this modem is transmitting back towards the left to its parent, the CMTS. So as you see here, the signal is characterized by the green arrow, where it's called main signal. It traverses through tap 17, comes out, goes left, goes through tap 20, and then when it hits the input of tap 23, we see that there is an impedance mismatch in this example. So what happens is the majority of the main signal continues forward to the head end, but some percentage, some subset of the original signal bounces back. Now this bounce back is traveling back towards the origin, which is the cable modem. And in this example, once it hits the port on tap 17, and this example finds another impedance mismatch. And as we spoke before, this will cause a microreflection. Now, this will continue many times back to tab 23 and back and forth. However, in the first round trip, because we know the rate and the time, we can actually find and measure the distance between two impedance mismatches. This is what's called the echo cavity. So let's step back a little bit about the echo cavity. And again, another analogy. I was looking at this information, and let's go back to 5th grade science class or math class. So in this math class example, little Johnny was in a car traveling 55 miles an hour, and the teacher says, how much distance will you go if you travel 1 hour? Well, you take the distance, which is 55 miles an hour, times the time, which is an hour, and the distance covered is 55 miles. Now let's take that same equation and apply it to the echo cavity calculation. So from each cable that is being used is categorized by velocity of propagation. So what's that? That is some percentage of the speed of light. Typically, it's 85 or 87% the speed of light. So that's your rate. Now, because of the information that we're gathering from the CMTS and the modem, we do have the time. Now, we don't need the full round trip delay time. We just need half the time. So we take the velocity of propagation, half of the round trip delay, multiply them together, and then we get the size of the echo cavity. So that is the calculation of how to get to the echo cavity. Makes sense? All right. So the question is, so why is this important? What does this really tell us? So we found, what is the echo cavity? So essentially, it allows us to understand the size of the cable segment or cable segments in which the impairment exists. Typically, if it's a larger span of cable segment or cable segments, we're going to say it's probably more on the outside plant. If there are shorter cable segment or cable segments, we're going to say it's a near home or in-home issue. So this is what the information that the size of the echo cavity tells us. So as you can tell, understanding what impedance mismatch is that concept is very important. What an impedance mismatch will produce, again, a microreflection, and then once you have multiple microreflections, then you have an echo cavity. Mm-hmm. So what does that tell us?
Got it. Okay. So when we were talking about the windows, I was actually thinking of another kind of example that might be kind of like that. So the greenhouse effect, right? So you've got sunshine going through a window, and it has no problem getting through that window, and it hits the ground, and then it bounces back up, and the signal changes, and it can't get back through the window. So it's really hot in a greenhouse. That's what makes a greenhouse work. Maybe that's an impedance mismatch. I don't know, but it's a signal, right? So,
absolutely. Yeah, absolutely.
Okay. All right. Well, this is great. So again, this is very important as far as PNM goes, because what the PNM tool is help show you where you have your impedance mismatch in a sense, or where your echo cavity is, and that gives you an opportunity to maybe go find the source of that problem. Once you can see where kind of your distance is, and you know where the first modem is impacted versus the first modem that's not impacted, it gives you an idea of where to start go looking for that problem. So next week, we plan on actually talking about in-channel frequency response, which is one of the charts that you'll see in a PNM tool. So when you're looking at a PNM tool, you'll see various kinds of things, table of information, some digital taps, which we'll talk about at a later time, and also in-channel frequency response. That'll be coming up next week. Thanks again for joining us. Thanks, Carlos.
Thank you. Yeah, and definitely, as far as this concept and these two terms, definitely meditate on this information, and then we look forward to talking to you again next week.
Okay, thanks. Bye.